So hello everyone. We're going to talk about the abstract syntax tree. So the talk title was a bit long, so I put a picture so you know you're in the right place. We're going to talk about what an abstract syntax tree is. So I'll use AST as a common abbreviation throughout the talk. And then why you should care, so some practical applications. And then we'll zoom in on some PyTest magic and how PyTest uses AST transforms to be a good library. And finally, we'll look at some usage of AST in data tools. So if we look at a simple expression like this one, we can start with the tree part of abstract syntax tree. This can be represented as a tree. So as human beings, we know to first evaluate the part inside the parentheses. And we can, the computer can translate that by representing it as a tree with a root node. So the multiplication operator is a root node. And then there's a left-hand side that's a subtree with plus. And the right-hand side is just 3 constants. And if you had to turn yourself into a computer, you might evaluate this by starting at the bottom and evaluating the 1 plus 2, and then evaluating the rest of the tree. So it's like a tree, except if you want to compare it, it's more like this tree, maybe. So if we look at this expression again, we can put it into a file and then use Python to tell us more about what the AST looks like. And this is what it spits out. So there's a bit more things here. There's a module. Basically, it's always the top level elements. This is because we put the expression into a file, to Python module. So it's a module. This module object has a body attribute, and there's just one element in the body list, and it's our expression. So yeah, here we're running the AST module as a script, and it just prints out the abstract syntax tree. So this tree, we can represent it here in a moderately nicer view. The interesting part is that every node is a Python object. So the tree itself is a Python object, and like nodes have attributes that are Python objects, so you can introspect these objects, and you can modify them. And you can like do all sorts of things with them. So we see that there are different kind of nodes. We see here a binup for binary operation, a constant node, and there are nodes for function definition, for import statements, for basically everything in the Python language. There's a corresponding node. So if we do a quick recap, the abstract syntax tree is a tree of Python objects that represents the source code. It doesn't depend on formatting, so if you have white spaces and like extra parentheses, they will be discarded. So we lose some information between the original source code and the syntax tree. So it's a useful representation of the code because we can play with it and modify it. So if we take a step back before we focus on the AST, and we could look at the high-level view of how Python source code gets executed. So this is so that you have an idea of like how things work, and you can dig into if you're interested. So Python starts by reading source code from a file, and this like stream of characters goes through the tokenizer and parser that eventually produces a parse tree that we completely skip here, and we pretend it's transformed immediately into an abstract syntax tree. And then this tree goes through the compiler that produces bytecode. So sometimes you see bytecode cached in PYC files after you run Python. And eventually this bytecode is what gets executed and runs your program. So if you're not like a software engineer or you're a bit new, there are many big words on this slide, on the previous slide, so don't feel intimidated. You can understand like the abstract syntax tree without understanding like everything about like what exactly the compiler does in this or what the bytecode consists of. And if you don't understand this reference, you can also understand the abstract syntax trees. So how do we use it? I said it was a useful tool, but how do we use the AST? Well, we can import the module, we take our expression, we parse it, and we get a Python object. Then we can like print it. So that's basically what we've done before, except in the interactive REPL. And another thing that we can do is we can unparse it. So unparsing gives us like source code back from the AST. Now Python doesn't really need that. So if you have a tree and you modify it and you want to execute it, you don't need to unparse it. Like Python can execute based on that tree. Unparsing is basically debugging convenience for developers. So now, say we want to modify the abstract syntax tree. So we can look at this example. This is straight from the documentation. So this is when you have a piece of code and you want to make it behave, like rewrite it on the fly. Make it behave like it was written a little bit differently. So the AST module gives us the node transformer class. That's well, it can be used to transform a tree. So it follows the visitor programming pattern. So we define like visit underscore and then the type of the node that we want to modify. So here we're visiting every node, every name node, and we are transforming it by returning a new value. So in this expression, b equals a plus 1, the name nodes are going to be like all the identifiers. So b and a are both name nodes. And then I guess here there would be a binary operator node for the plus thing and an assignment node. But usually, like when you work with this, you can look up the type of nodes that you need as you go. You don't need to know all of them beforehand. So the subscript node here is the square bracket index access. So what we are doing is we are transforming this expression, like the name node. So when we access B and A, we transform them into something different, something that is a subscript access on a data object. So basically, if we run this transformer, we will get code that is equivalent to this, data B equals. So it's going to replace all variables access with this subscript syntax. So the interesting part is just that it's a simple example, and yeah, it shows that it can, like with a few lines of code, we can modify like, our source code in pretty powerful ways. So now let's look at a real world use case. That's a little bit more interesting. So maybe you do testing in Python and you know that you don't really need a library, right? You can write your code and you can write your tests and you can just run the test, and Python gives us assert, so we can like work with that, and it works fine, right? So, but when we run this, it's a good test, so it fails because there's a bug somewhere, but it just tells us assertion error. That's all we get. So this is not very helpful, right? What we'd like to know is like, okay, so the string is not what we expected, but what was it? Was it a string? Was it like none? Was it undefined is not a function? Or what was our result? So it can get a bit worse, like if you have a more complex expression and here you don't know what A is, what expected was, you just get assertion error. So now imagine like the bug happens only when you run the full test suite in sequence and only once every 5 test runs. Or so this makes the typical like professional software engineer developer experience of adding print statements and like running the thing again. This makes it a bit tedious, right? Now, what happens if we run it with PyTest? So this isn't a PyTest ad, but it's pretty cool. They just print like what a helpful computer would do. Like if the computer actually was our friend, it would like tell us, okay, so there's an assertion error, but here's what's on the right-hand side and what's on the left-hand side. So it might look like, it doesn't look like much, but like, how did that happen? Because PyTest just ran the code. I mean, we gave some code to PyTest. It was just an assert statement, and PyTest managed to print out this very helpful message. So what happened is that PyTest modified the code just before executing it, and so that it could print this nicer error message. So now the next question is, can we do it? Can we do something similar, maybe? as like what would it take to build a better assert statement into Python, like kind of the way PyTest does. Well, we know we can modify the abstract syntax tree to run like different code. So we get source code, it's parsed into an abstract syntax tree, we modify it, and then we run that modified code instead. So we know we have this tool. So a good starting point maybe is how would we want to modify the code? So I'm going to say that we want to build something like this. So it's similar. We get an assertion error, except that we get a breakdown of like what the intermediate values were at each step of the computation inside the assert statement. This is like a poor person's PyTest, basically. So we will want to print intermediate variables, right? So we start with what we have to work with is this assert statement. And what do we want to replace it with? Well, we want to print intermediate variables, so maybe we'd like it to behave as if the code Python was running was not just this assert statement, but instead was like a series of statements where it first computes intermediate variables. And then the assert statement uses these intermediate variables, and if it crashes, we print out the values. So that means we would use an abstract syntax tree transform to go from these assert statements to the series of these 10 lines or so of code. So yeah, one thing is that we also want to print, here we're printing values, we also want to print the names of the variable or where they come from. So maybe we can just like use a tuple and stuff everything inside the tuple so that we have the description of the variable and then the value. So we know we want to rewrite assert statements, so we can start like this. Like we know replace assert nodes with more complicated stuff. That's a good starting point. And then you just like tab and hope Copilot or someone else does it. But it's a good starting point. Like visit assert nodes, and we know that we need to replace the assert nodes with a list of nodes. Or here, I mean, I'm building something a little different but we'll see what goes into it. So first, we want to collect the intermediate variables that we want to have defined. Right? So let's look at the big picture first. So as a first step, we collect the intermediate variables, and then we construct the except block. So that's like the except part of the try except. And we know that we want to print the assignments that we have. So all our intermediate variables, we want to print out their name and their values and add a raise statement at the end. And finally, we put everything in a try statement. So that's a little bit different from what I put on the previous slide. It's like all the intermediate variables definitions are inside the try statement. So the tricky part is that when collecting the assignments, we need to visit everything that's under the assert node, because if you remember what we have like square A, B. So the assert node is the top level node essentially in that expression. And then we have to go down all the way to find the function call nodes to know that like there's an identifier that's A and like a name node for B, and we want to collect all of these. So for that, we can use another transformer. The details of this part, this is not critical. I should have blurred this one actually. Just you're probably blurring it on your hand, so it's fine. But it's also to show that all the code fits on slide, sort of. So it's not, at the end of the day, it's not that complicated. So this takes basically the assignments nodes that we have, and it just like spits out the print nodes that we want in our resulting tree. So to collect the intermediate variables that we want, we can have like have another transformer and just basically write code that doesn't need to be pretty. It just needs to do the job. And sorry. So yeah, we visit. Sorry, I went a bit fast. We even for me, sorry. We want to visit every call node and every binary operation node and collect assignments and give them nice variable names and with the relevant values. So first we get a variable name, variable ID for the node we are visiting. And so yeah, this can be like maybe we add a variable prefix so we know where it comes from, and a counter to make sure it's unique. So this is basic like accounting to avoid issues. And then basically we have what we need. We just know that like the node needs to have like the node can use the variable ID that we want, and as a value it can use the value of the original call. So the generic visit just makes sure that we visit the children of this node because we want to go all the way down. And yeah, this is again accounting. So one interesting part is how we name our variable. So we said earlier that we can use a tuple to store the description of the intermediate value we are computing. But it turns out we can also put that description just in the variable name. So this shouldn't really be allowed because here this means that we are going to call our variable like add parenthesis AB, so, which isn't really a valid Python name. But it turns out that once the parsing step of Python has been like done, you can call your variables anything you want in the abstract syntax tree, and Python will happily execute it. So because all the ambiguity was at parsing, so now we can just like call our variables anything we want. So is that a good design decision? I don't know, but we can do it. So. So this is what the resulting code looks like after transform. So you can see that the naming of variables makes things a little odd. So this is the output of ast.unparse. And this is not valid Python, but Python will be happy to execute the associated tree that we had. It's just that ast.unparse is not like it's not a two-way transform that like you cannot necessarily parse the result of ast.unparse. So our first variable, for instance, is called intermediate3 expected -1 with spaces in the name of the variable. So, but if you omit that part, the code is relatively simple and it's like similar to what we wanted. So I'm sorry because it was a lot of code and even I got confused at some point. So that kind of tells the story. But that's basically all of it. And so what's the link with PyTest? Well, if we look at PyTest, it's pretty similar actually, the result of what their transform is. So we had a lot of code, so here's some more code. And this is what happens when we unparse the tree after transformation by PyTest. So we can see that they have also intermediate variables, right? The at pyassert1, those are intermediate variables, and then they do a bunch of things that makes sure that a nice error message is printed when there's an error. So they're not using a try except, they're using like they're putting the assert in a boolean, but it's very similar things. And it's also similar in the fact that at pyassert1 equals world is not valid Python. So they're using the at symbol in their variable names. This is a way, I guess, to avoid conflicts with like user variables. And so Python cannot execute this code, but the tree that gave us this code works just fine with Python. So I think this is an interesting example because it shows that at the end of the day, it's not that complicated. And yeah, I think I found it a very empowering example when I learned about it. So yeah, there are some references. The code for PyTest is actually readable. I don't understand everything in detail, but like I don't want you to be limited by my shortcomings. So I wanted to show that the AST are used in popular tools. They're also used in like interpreters, linters, yeah, like ESLint in JavaScript, flake8 in Python, formatters like Black, they use the AST. It's useful when you want transpile, convert from one language to another. Template engines like Jinja2 is one example of a very clean code base and that passes the templates into an AST. So I think it's a fundamental concept, not because it's simple or it's basic, but because it powers a lot of the tools that we use. So one example that I'll go over quick maybe is automated refactoring. So sometimes it's called code modifiers or code mod. It's a script that takes old code as input and outputs refactored code. I think it's a nice starting point when you want to sometimes learn about the ASTs. You have a very boring refactoring task to do over a large code base, and you can automate some of it, it turns out. So knowing that you can automate some of it might make you prompt to look for tools that already do what you want. So already knowing that it can exist is half the battle. And yeah, if you do want to do refactoring, I advise using like a library, probably using a concrete syntax tree, because like the abstract syntax tree doesn't preserve comments and you don't want to anger your coworkers. So yeah, the steps might be look for existing tools. A nice thing is that you can write ugly code when you're refactoring because it's a one-off script basically, so you can throw it away afterwards. Don't worry about formatting because it makes like I would outsource formatting to a formatter so that the script doesn't have to care about that. And you also don't have to go all the way. You can handle edge cases manually. So if your script takes you 90% of the way, that's already great. And finally, a bit about AST and data tools. So I thought at this stage, like I was pretty sold on like how powerful the AST was and AST transforms. So I thought they would show up a lot in data tools, and it turns out not as much as I thought. So I was looking for, I thought I would find tools that use it for core functionality, not just linting or static analysis. So I didn't really, but I'll mention a few examples of what I encountered. So there's pandas, like the data frame library, and there's this query function that takes a string. And there's a lot of magic going on here, where you just pass it a string with a greater than b, and it's going to filter the data frame based on the columns. So to do this, like pandas must first parse the expression. So they use Python parsing for that. And then they tweak the AST to use pandas columns for A and B. So it relies on Python parsing to do that, but they have to like tweak it a little bit because they also allow weird expressions like these, where like there are spaces in the column name, so there are backticks, which is not valid Python syntax. But they're like, this is an expression, so they still need to parse it. So the parser will reject it if they use Python parser. So this is a valid example, but it's also a bit of a niche feature, I guess, because I would use the latter example. So I don't know, I don't know what people use, but I feel like it's not core functionality in pandas, so it's more somewhat on the side. So I look for more examples. So that's a project from Simon Willison. Like a very like famous, like, I think Django developer and blogger, and it's a way to search Python code, and like with the purpose of feeding into LLMs. So yeah, so this is a sample of how it can be used. The code base is very approachable. It's like a few hundred lines and regular Python, so that's a good place to to look at. Another tool that's kind of similar is it's also like I included it because it's a simple tool that's I mean there's a bit of magic, but the code base is also very approachable. So it's basically it lets you run Python in the command line to replace cut, sed, awk, and you can see that you tell it to take like x and you index into it, but what is even x? What is line and so on. So they have to do a bit of magic to do that, and they do this by transforming the abstract syntax tree to like add variables and stuff like that. They also they also add imports. So if you use RE, regular expression package, they import it automatically and so on. So this is all abstract syntax tree magic manipulation behind the scenes. And finally, Dask, a parallel computing library. So here it was just used in one place. I was a bit disappointed to find that. But it's a nice trick. It's how they interpret environment variables. So this basically lets people define dictionaries in environment variables as strings, which you may or may not want to do. But yeah, it's safer than just using eval and evaluating every kind of like user code. So thank you. I hope that I helped demystify a bit the concept of the abstract syntax tree. It might sound a bit scary the first time you hear about it, but it's actually quite approachable, and it gives you a lot of power for things like automated refactoring. And so, yeah, you won't necessarily use it every day, but knowing that it's there, next time you have a boring migration to perform on your large code base, then maybe you reach out for it. Thank you.
Any questions? Yeah, on that side already.
Thank you for your nice presentation. I experimented using AST in Python, trying to move Panda naive code to method chaining automatically. It works. But what I notice is that when you change the Python version, sometimes the abstract tree change for a standard Python operation. And so you have to, not to rewrite all the code, but to change somewhere in the code because I don't know, some operator is not represented the same way when Python migrate. It was from Python 9 to Python 10 and so on. And so I want to know if you have experimented such problem.
So yeah, you are correct that the abstract syntax tree is not like completely stable, so it might evolve. I guess that's why maybe it's not used as widely as I thought it would be in data tools, because they don't want to pay that burden of maintenance. I don't really know of a good solution. I guess test cases and
First of all, thank you for the talk. I was thinking about the rewrite assert transformer that you showed, in particular that once you started working with AST, you were forced into using that kind of syntax. For example, I'm trying to wrap the assertion in a try except block. For me, it would be nice to see the try except the way I'm used to seeing rating. Do you know if there is a nice way to mix both kinds of like style?
Yeah, I think that's a good point. So I guess the point, if I rephrase it a little bit, is that if you want to transform like one line into 10 lines, it's very hard to write the 10 lines with like as 3 statements. It's much easier to like if you write a template and just like fill in the variables, it will be like much nicer. I think there are ways to do that. For sure, like if you're adding. I mean, yeah, so sometimes you can mix and match a little bit and use AST parse on a small bit of code. And then you can use the nodes to construct your AST so that, yeah, you don't have to do all the tedious construction yourself. I'm not sure, I'm not sure how generic a solution we can find here, but yeah, definitely something to keep in mind is like, if you can like not have to construct the AST node by node, and you can just like parse a big chunk of like, templated code, maybe that's a nice gain of readability.
We have one other question here.
Hello. So thank you so much for the talk. I didn't know you could do that in Python, and I was wondering if you could kind of hack around with it, because it remind me a lot of Rust macros. So if you could do something like that, like modify syntax or those sorts of things.
Yeah, definitely. I mean, there are macros in Python. I can send you a link later if you want. There's a proof of concept using the abstract syntax tree for macros in Python. If you want to add syntax, I think you need to do a little bit more. Part of it is adding support inside the abstract syntax tree, but also like if it breaks, like if Python doesn't want to parse the code, then you need to do some extra work. But yeah, I can send you if you're interested.
Thank you for the talk. I noticed a lot of the use cases were around modifying code before you pass it off to the interpreter. So in the case of PyTest, like adding more context, etc. Are you aware of any use cases where you can actually get insight around your code from the abstract syntax tree, such as around like performance improvements or that sort of thing?
Yeah, so it's used a lot in linters, like Flake 8, or like when you get the little squiggles in your IDE. You can also write some custom like linting or static analysis scripts with like AST just visiting the trees. You don't need to transform it. So I think it's a good tool for that. For performance, I think it's used sometimes, but I cannot. Like, I'm not knowledgeable on the details of how exactly it is used. So yeah, something to dig into, but I guess it can be also a tool for that.
Any last question? Okay, then we can thank our speaker again. Thanks.